Okay, now that we've taken a very close look at vectors and various vector operations, it's now time to start talking about matrices.
That's right.
Matrices are going to play a very important role in many of the calculations we're going to do when creating a graphical application.
Right. When we're doing things like projections, transformations, all of that requires the use of matrices. And if you don't understand how they work, doing anything inside of OpenGL is going to be a real difficult thing.
That's right.
You'll have this huge block.
As a matter of fact, if you think back to the introduction video in this VTM, we even talked about resetting the matrix.
Right, we reset the model view matrix with the load identity function.
There you go. That was a very important part of the entire workflow in creating a graphical application.
And a lot of people that use OpenGL simply kind of skim over that entire fact and just kind of look at the functions, take it for granted. And if you don't really truly understand what's going on behind the scenes, you can never fully utilize the power of OpenGL. And understanding any API like OpenGL DirectX, you need to understand how matrices work and how transformations work in general.
That's right. So let's start simple. What exactly is a matrix? In its most raw form, it is nothing more than a collection of numbers divided up into rows and columns.
That's right.
That's it.
Right. If you're a programmer, you probably use this a lot. You have basically an array inside of an array, which allows you to have numbers and rows and columns, or even more dimensions if you wanted to.
That's right. Now, in our case, since we're, of course, studying graphical application development, matrices are a collection of vectors.
Right, and they allow us to do transformations, which basically stores inside of a matrix. Well, in OpenGL's case, it's a 4x4 matrix.
Okay.
That allows you to store the coordinate axes, how we're viewing the world, or how the world is oriented.
Cool.
And that's what we basically can do with matrices. And what's cool is it holds all of those numbers and all that information in a really condensed form. Instead of having 3 vectors or 4 vectors that describe your entire scene, you know, how it's oriented, you have one matrix that describes the entire thing.
Right.
Which can be very, very powerful and useful.
Absolutely. So let's go ahead and first get them familiar with what a matrix looks like.
Right.
And when you're saying things like 2x2 and 4x4.
What is he talking about?
What's he talking about?
Exactly. So let me give a few examples of matrices. And the first, most simple one, let's give a 2x2 example. So we have brackets surrounding our matrix, first of all, and we can just put any kind of numbers in here. We have 5, maybe 2.3, -6, and 5. I just want to put
generally, when you refer to a matrix and you say it's a 2x2, you're talking about rows then columns.
Right. So right here, we have our rows. And right here, we have our columns. And
reading them out, when dealing with a collection of vectors, it's pretty common to read columns, then rows.
Right, so we have 5, 2.3, -6, and 5.
Right, so 5 and 2.3 is our first vector. And
or if it depends on which field you're in. Sometimes you'll refer to, well, in OpenGL's case, typically this first column will be our X.
Right.
And this column here is going to be our Y.
All the way down.
Exactly. So we would have, say, 5, -6 for our X, and so let's say this is X, and our Y would be equal to 2.3 and 5. Something like that. So it depends on how you use it, but essentially, remember that in this case we have a 2x2 matrix, so 2x2. And if we had something like, let's say, something maybe 5, 2, 3, 1, and another one 7, 8, 3, 2, this is going to be
4x2.
Right. Remember, we have 4 rows, so 4 rows and 2 columns down here, so 4x2.
Cool.
So just so you know exactly how that works. Now, what if we wanted to do certain operations on matrices?
And there's quite a few of them, actually.
Yep,
we can swap rows, we can add rows, we can multiply a row by a scalar. Heck, we can even multiply an entire matrix by a scalar if we wanted to. There's adding and subtracting different matrices, if we wanted to work with multiple matrices, and then there's multiplying matrices, and there's some rules that we need to follow.
That's right. So let's go ahead and first look at swapping rows around.
The easy stuff.
Right, exactly. A lot of times when doing operations like this, people will label like the first row A, the second row B, C, and D all the way to the bottom. And if we wanted to say maybe add these A row and B row together and put the final result into A, right? So we could do something like B plus A, and then do an underline under A. In other words, put the final result of this addition into row A. So we would have 5 plus 2, which is 7. So this would get replaced with 7. And 7 plus 8, which is 15.
And that
so
replaces
this would get
7. And row B remains the same.
Exactly. And we could do subtractions as well. So let's subtract these two rows and put the result in C. So we could have, say, B minus C.
Underline C.
And then what we would have is 2 minus 3. And that will give us a negative 1. And 8 minus 3 will give us a 5.
5. And, of course, row B remains the same.
Exactly. So that's one thing that we can do, adding or subtracting different rows. We could swap rows around. We can swap, say, B and D around.
We just draw, a big old curved arrow thingy.
And so, in this case, let's actually draw our new matrix down here, just to make it a little bit easier.
So, basically, we've got 7, 15.
We have 7, 15.
Now, 1, 2,
negative 1, 5. And then 2 and 8.
You can see how basically we've represented A and C with the new values generated from the two formulas we applied above. And then we also represented B and D, rows B and D, with the swapped values.
Right. And for those of you that are familiar with algebra and so on, this is a common way in which you can go about solving sets of linear equations.
That's right.
And this is a lot of the operations you would need to do that with.
Cool.
So other than that, how would we go about multiplying an entire matrix by a scalar? Now this is extremely easy. Let's say we have a 2 by 2 matrix, 1, 5, 7, and 2. And I want to scale this entire matrix up by a factor of 3.
Okay.
So I can say simply 3
times
this 2 by 2 matrix here.
And you're just going to basically go through and multiply 3 by every
single one. So 3 times 1, 3 times 5, 3 times 7,
so 3,
and 3
15,
times 2.
21.
So 3, 15,
6.
21, and 6.
Nice.
So that's our final matrix. Now, these are all very, very simple operations. What if we want to add or subtract two matrices?
Okay.
This is really easy as well. Let's go ahead and erase some of this.
Okay.
So let me just make a little bit of room for myself because we're running out of whiteboard space. Let's have a 3 by 3 matrix. So let's say 5, 2, 1, 7, 3, 2. Now let's make it 3 by 2. Because I'm getting lazy.
That's right.
The first thing you have to understand when adding and subtracting matrices is that they have to be exactly the same size. It just does not make sense to add a 3 by 2 matrix as we have down here with a 2 by 2.
Exactly.
I mean, what do you add?
Right.
So basically you would be adding each cell, if you will, to the other cell of the other matrix. So if we have 3, 6, 2, 1,
5,
9, 5.
There you go.
So if we add these two together, simply take the same cell of each one and add them together.
That's right. So you're going to end up with 8, 13, and then 4, 4, 10, and 7.
Very good math skills.
Show me the apples, baby. So yeah, there's what you end up with.
And the same goes for subtracting as well.
Yeah, exactly the same thing. Okay, so that's pretty simple. Mm-hmm. Now let's go ahead and talk about multiplying two matrices together because this gets a little bit more involved.
Yes, it does.
A little more tedious, to be honest.
Definitely. And the first thing is, what kind of matrices can be multiplied together? The rules become fairly strict when you start worrying about multiplying. So let me just move down a little bit. If we have a 2 by 3 matrix, we can only multiply this by someone that has the same number of columns for rows. So it's switched around.
Right.
So if we multiplied a 2 by 3 by a 3 by 4, it would work because these two elements match. And as long as they match, then it can be multiplied together. And your resulting matrix would be a 2 by 4. So you take the diagonal to calculate which it would be.
That's really cool how that works.
Very, very cool.
Interesting.
So this was a 3 by 4. So let's take a quick example. Let's say 2 by 2 and 2 by 2.
Yeah.
Something simple.
Let's start with something simple.
So let's say 7, 2, 5, 3. And we want to multiply this. I'll just represent by a little dot. And 2, 5, 6, 4.
Now, I've been shown a really interesting way to go about multiplying matrices together. And it's using the giant plus symbol.
Yes, a giant plus symbol. Let's go ahead and just kind of put an arrow over to here where we actually do our work.
Okay,
but this is our goal.
Why don't you erase all of this and all of this?
Okay.
That'll just give us a lot of room to work with. Then you can do it all right above it.
Okay. So let me just erase all of this.
And use the old shift key and draw a giant plus.
Whoop. No. Giant plus. And what we're going to do is put
one matrix into the bottom. So it's like, what, quadrant 3?
Yep, 7, 2, 5, 3.
And then we're going to put the other matrix in quadrant 1.
So 2, 6, 5, and 4. And to multiplying two matrices is much like taking the dot product of a row and a column of each matrix. So what we're going to do is take this row of this one.
So go ahead and draw your line. This is what's really cool right here.
So we draw a line, and we draw a vertical line from the other matrix all the way down.
And where these two intersect, that's going to be the two sets of numbers we're going to more or less find the dot product of.
Right. So what we're going to do is take the dot product of, I'll just draw in this area right here, 7, 2, dotted with
2, 6.
And of course, we all know how to do this.
You guys remember how this goes from the last video, so it's 7 times 2.
So 14 plus 12.
Plus?
Yeah. So 14 plus 12 equals
you
26.
Ahead. Okay.
Yeah.
I'm used to you carrying it down step by step.
Oh, sorry. I just kind of skipped a few steps there.
And so I'm like looking behind me, just listening to you, and all of a sudden it's like, whoa!
You already did everything. So if we take the dot product of these two vectors, we get 26.
That's right.
And this is going to go in this cell right here. So let me try to just erase this.
So at this point, guys, Joel is expecting that you completely remember how dot products work.
Yes, I am.
That's right.
So we do the same thing.
All the way across now.
Grab all the way here.
7,
right
2 dotted with 5, 4.
So 7 times 5.
35
so 35 plus 8. And that's going to give us a number. 43.
That's right. So now that I see you're going all the way, it's not a problem. Now we're going to do the same thing with the bottom. So
5 times 2.
Yeah, and you can just get to where you do it in your mind. So you're really looking at 10 plus 18. So it's got 28. And then you're going to dot 5, 3 with 5, 4. So now you're looking at 25 plus 12.
Which is going to give us 37.
That's right.
So our final matrix, let me just put it down here,
is 26, 43, 28, 37.
And hopefully you can see exactly how complicated this can get the larger and larger matrices you have.
Yeah.
If you had a 4x4 matrix, I mean, you're looking at, 16 dot products with 4 size element vectors, which can become very, very intensive and very difficult to do manually, hence why the simple example.
Though I would like to show them one other thing. Right now you just did a simple 2x2, and of course a 2x2 can be multiplied with a 2x2 because if we cross the two 2's, they match, and the result is if you cross the other two 2's, they could draw that out real quick just so you see what I'm talking about.
So if you have a 2x2
and then a 2x2
and a 2x2.
Now remember, you go from the upper right to the bottom left, so they match. So we can multiply them,
and our result is a 2x2.
And it's exactly what we got.
Right.
Now let's go ahead and give them.
Let's do a 1x3.
Okay.
And a 3x1.
Okay.
Do you see what that is, though? I mean, that's simply two vectors that we're multiplying together.
You're really wanting to stay lazy.
Well, let's make it. Okay. Let's make it a 2x3.
Touche.
And a 3x2.
Okay, that's cool.
And so, of course, these two match, and we're going to
end up with a 2x2.
That's
again. Cool.
So let me erase all of this, just because we're starting to run out of room. Let me just delete the whole thing. So what I say?
So upper left-hand corner, like a 2x3 and a 3x2.
Let me make the giant grid again, just to make it easy. Giant grid.
That's giant. So upper far left-hand corner, right.
Here, does one you mean?
I'm thinking up here, just a 2x3, 3x2. No, I was just going to say that you're just writing out that's what we're going to do.
Okay. Right. Okay, so 2x3.
Yeah.
And a 3x2. So this first one right here, we're going to have 2 rows and 3 columns.
That's right.
So let's do something like so. So 2, 5, 7, 6, 10, 3. And over here, we'll do a 3x2.
So 3 rows, 2 columns.
1, 6, 2, 3, 5, 1. And just so you can see how this works out. So we draw a line
right through
here, match it with this one right here.
And then, of course, the dot product. So we're going to have
2 times
plus
1.
30 plus 14.
2 plus 30. 2 plus 40 times 14.
Times 14.
And plus 14, excuse me.
I gave you all that a second ago.
I know.
So good.
44 plus 2 is going to give us 46. So let me just erase this and put in a 46.
That sounds good.
And then we can just do the rest of these in our head. So, no, we won't
Go
do
right
it.
ahead. I'm not that good with math.
6 plus 25 plus 7 is going to give us 38.
Okay.
And then
we'll just go down and do the
same thing
exact
with this
same
one.
thing. So we're going to have
6
plus 60 plus 6.
A lot of 6s there.
Yes.
So that's going to give us a 72.
Okay, and then we're going to have 18.
6 times 3, which is 18.
So 18 plus 50 plus 3.
So that's going to give 68 plus 3.
71.
70.
Woo!
So our final matrix here is going to be a 2 by 2.
That's right. So it's 46,
46, 38,
72,
72, and 71.
Isn't that cool how that works out?
Yes, it is.
So we took a 2 by 3, multiplied it by a 3 by 2, and look at the result.
Right, and very soon you'll see us multiplying 4 by 4 matrices by 4 by 1, which will allow us, if you see here, we have a 4 by 4, and we multiply that by a 4 by 1, which is going to give us a 4 by 1, which is our final vector.
Right.
In other words, for our 4 by 4, it's going to be our transformation matrix, and we multiply that by some point which transforms that point to a new location. So that's basically how we're going to be utilizing all this stuff we've just looked at.
Right. Again, this stuff's going to become very important. Now, order. So if I said take matrix A multiplied by matrix B.
Are they going to be the same?
As matrix B multiplied by matrix A.
Right, and so just to make this clear, let's say we have this one as, this is matrix A, and this guy here is matrix B. What he's saying here is that if we have A and multiply this by B,
would the result
is this
be the
equal
same?
B times A?
And the answer is no.
The answer is a very no.
Right.
There are some cases when you're working with the identity matrix, which you'll see in a few minutes, then it would be the same.
Very rare cases.
It's a very rare case in that when you multiply two matrices together, they're commutative. In other words, they can be done like this.
Right.
Typically, this is not equal. These two operations are not going to be equal. And this is very important when you start working with matrices and transformations. Your dot products completely change around.
That's the bottom line.
Right. So you get a completely different result. And I mean, in fact, if we switch this around, notice we have a 3 by 2 and a 2 by 3. Even the size is different. This is the same, but we end up with a 3 by 3 matrix, which is completely different.
Exactly.
So as long as you keep that in mind when you start working with things, if something is completely messed up in your final result is just completely whacked out. Maybe you had completely different operation. Right. It was multiplied in the wrong order.
Now that's really all there is that we wanted to talk about matrices. It's really straightforward, to be honest.
Very simple.
As long as you guys have a good grasp of dot products from the last video.
Right.
And you understand that in our case, a matrix is nothing more than a collection of vectors.
Right.
And then how we can take these two different matrices and multiply them together by using dot products and using this little formula right here with the giant plus symbol that we can divide things up with. You guys should have absolutely no problem following along with all the different matrix operations we're going to be doing throughout the VTM.
That's right.
So with that, that's pretty much going to wrap up this video. Thanks a lot.